Now, let's discuss your different circuits, which now involves your inductors. The first type of circuit that we are going to discuss is your RL circuit, or your resistor inductor circuit. An RL circuit contains a resistor, an inductor, and possibly an EMF source, of course. They are commonly used in chokes of luminescent tubes, and in an AC circuit, inductors helps in reducing voltages without the loss of energy. Due to the inductive reactance, the higher the AC frequency, the greater the impedance of the inductor. And under the recurrent conditions, an inductor acts as a static resistance. Now let's analyze your RL circuit shown in the figure here. You have here again your resistor, which is in series with an inductor. You have some EMF, your source of your potential, and then switch S1 above, and you also have another switch S2 below. Now let's start with closing switch S1, and the moment you close the switch F1, this is close. The moment you close switch S1, your current flows in your circuit only on this one here. And remember that we let your S2 remain open. Again, if you close switch S1, your current flows in your circuit. However, as you can see, you have your inductor here. And as discussed earlier, your inductor opposes the change in your current. So that means your current flows, however, it cannot change suddenly from 0 to some final value because your inductor here resists your current flow, or it resists the flow of your current. And if there was no inductor here, the actual current is equal to epsilon over R from your Ohm's law. But you have your inductor here, but since you have your inductor here, then the current that flows initially in your circuit is less than your maximum epsilon over R. We're still talking about the one where S1 is closed. If you're going to apply your Kirchhoff's loop rule here, say let's move around this path. Let's travel counterclockwise. The moment we close S1 there, so you have your Kirchhoff's loop rule according to this equation here. The first you have your epsilon minus your IR, since your current flows flows through this direction. So you have minus IR minus the voltage here, which is your LdI over dt. So you have minus LdI over dt. Since we don't have any other circuit component, so you have your epsilon minus IR minus LdI over dt that's equal to 0. From here, let's solve your di over dt by playing with the equation. So you have your di over dt that's equal to epsilon minus IR over L. Or you have your di over dt that's equal to epsilon over L minus RL times I. Applying some boundary conditions at time equals 0, the current I is 0. So again, the moment you close the switch, you have your inductor here, which is the sudden change in your current. At time equals 0, the current I is equal to 0, and the potential drop across the resistor is actually 0. We don't have any current here yet. So if that is the case, if at time equals 0, your I is equal to 0, from this equation here, there is no voltage in your resistor, so this is 0. So at time equals 0, your di over dt, or your time rate of change of your current initial, is just equal to epsilon over L. And as you can see, the greater the inductance, the more slowly the current will increase. So if you have a greater inductance L here, this rate of change will be more slower as you can see in the equation. So again, the greater the inductance, the more slowly the current increases. And as your current increases, though uh, though your inductor opposes the sudden change in your current, it will also allow, or what will happen is that there is a gradual change in your current instead of the sudden change of your current. Because your current increases, your di over dt approaches to zero. So this one here, your di over dt approaches to zero. And if that is the case, if your di over dt is now zero, then you have your zero that's equal to epsilon over L minus RL times I. And playing with the equation here, you have your current that's equal to epsilon over R, which is the maximum current that your circuit can attain. So again, at time equals zero, there's no current yet because of your inductor here, which resists the sudden change of your current. But as your current increases, as time goes by, this change in current di over dt here approaches to zero, and then your circuit can now attain the maximum current possible, which is equal to epsilon over R. Now let us go back with this equation here, and let's discuss the current growth in your RL circuit. So you have your di over dt that's equal to epsilon over L minus R over Li. Let us rearrange this equation to have this form. You have di over I minus epsilon over R is equal to negative R over L dt. So in order to solve this equation, we will integrate both sides, but upon integrating, let us change the integration variables I prime and t prime so that we can use I and t as the upper limits. So instead of di, you have your di prime. Instead of I, you have your I prime. Instead of dt, you have your dt prime. And our upper limits are your I and then your t. The integral of this side here, of the left-hand side, is equal to ln of I minus epsilon over R over negative epsilon over R. This one is already evaluated from 0 to I. The integral, on the other hand, of this side here is equal to negative R over L, also already integrated from 0 to t. So you have this equation here. This is just the same equation earlier. And if we take the exponentials of both sides, that is, take e, both sides. So this one, so what will happen with this side here, it's just you will just be left with your I minus epsilon over R over negative epsilon over R. And then on the right hand side, you have your epsilon, or sorry, you have your E minus R over LT. And after taking the exponentials, we solve for I. Solving for I, you have your I that's equal to epsilon over R times 1 minus E negative R over L times T. So you just did some algebra here to have this form here. This one, this equation here, this is the current in an RL circuit with an EMF. So what happens is you have this current growth here. So it does not start automatically from maximum current, which is equal to epsilon R, but it starts with 0, and then there is this exponential gradual change in your current. And again, this is because of your inductor, which opposes the current change in your current. With the same equation for the current in an RL circuit with EMF, Let us take the derivative of this equation here. So the derivative is you have your di over dt. Taking the derivative both sides, you have your here, just to show you, you have your d over dt, and then also take your d over dt here. The first thing here is a constant, so you just need to take the derivative of this side here. Okay, so taking the derivative, you have your di over dt that's equal to epsilon over L times your exponential of negative r over L times t. Looking from here, from this equation here, at time equals 0, if you're going to change here, your time is equal to 0, your di over dt is equal to your epsilon over L, because this is just 1 when t is 0. As time approaches infinity, as time here becomes bigger and bigger, your um, your I approaches to epsilon over L, and your di over dt approaches to 0, as we have predicted in the introductory discussion of your RL circuit. The instantaneous current I first rises rapidly, then increases more slowly, and approaches the final value I that's equal to epsilon over R asymptomatically, or asymptotically, sorry. So at the time equal to your L over R, the current has risen to 1 minus 1 over E, or about 63% of the final value, which is around here. And that quantity is therefore a measure of how quickly the current builds towards its final value. And this quantity, your L over R, is called your time constant for the circuit, denoted by your tau that's equal to L over R. For the power in the RL circuit, we just multiply your EMF with I, and it's the current, so you have, or that's the power, I mean. So the power in the circuit is equal to your epsilon I, your EI, that's equal to I squared R, plus Li, di over dt. Some of the power radiated in the resistor here, and some power are stored in the inductor. Let's have an example. A sensitive electronic device of resistance 175 ohms is to be connected to a source of EMF of negligible internal resistance by a switch. The device is designated to operate with a 36 milliampere current, but to avoid damage to the device, the current can rise to no more than 4.9 milliamperes in the first 58 microseconds after the switch is closed. An inductor is therefore connected in series with the device as shown in the figure here. The switch in question is S1. What is the required source of the EMF? What is the required inductance L? What is the RL time constant tau? Again, a sensitive electronic device of resistance 175 ohms is to be connected to a source of EMF of negligible internal resistance by a switch. The device is operated, or the device is designed to operate with a 36 milliampere current. But to avoid damage to the device, the current can rise to no more than 4.9 milliamperes in the first 58 microseconds after the switch is closed. An inductor is therefore connected in series with the device to avoid the device to be broken or damaged. What is the required source EMF? What is the required inductance L? And what is the RL time constant tau? So these are your given. You have your resistance 175 ohms, your current 36 milliamperes. However, this current is limited to 4.9 milliamperes in the first 58 microseconds. The first Task is to find the required EMF. So your required EMF is just equal to your current I times R, which is equal to 36 milliamperes times 175 ohms, which is equal to 6.3 volts. Next, let's find the required inductor. From this equation here, your current is limited to 4.9 milliamperes in the first 58 seconds. So we just use the equation for your current I at time 58 microseconds. You have your current is equal to 4.9 milliamperes. So this one here, this is 4.9 milliamperes. That's equal to 6.3 volts times 1 minus e to the 175 divided by your L times your, this is your time in seconds. So your target here is to solve for your L. You can solve this one by taking the natural logarithm of both sides of your equation, and you get your L, which is equal to 69 millihenries. Since you have here your milliamperes, you can just directly use your millihenries here. Lastly, what is the time constant? So your tau is just equal to your inductance over your resistance. So you have your time constant tau that's equal to 390 microseconds. Now let us have your current decay in an RL circuit. Now suppose the switch in the circuit has been closed for a while, your S1 here has been closed for a while, and the current has reached the maximum value, which we will call your I naught, which is equal to epsilon over your R. Now let's close the second switch, S2, and while we close S2, we also open your S1. So we close S2 and then you close your S1. Now this time, the current decrease is opposed by your inductor. Remember that initially you have your current I naught in your circuit, and once you open S1 and close S2, your current will decrease. However, this current decrease is opposed by your inductor. Again, your inductor opposes any sudden change in your current, so it will not immediately go to zero. There is an EMF that is generated to keep the current flowing in the same direction. Thus, the current doesn't drop to zero immediately. And again, this is because of your inductor here. As we close your switch S2 and open S1, we are left with this circuit here, which is only your resistor and then your inductor. And as you close switch S2, again, the current does not go to zero immediately because you have your inductor here. From your Kirchhoff's loop rule, and following this travel here, clockwise travel, we have your minus IR for your resistor, and then minus L over L times di over dt for your inductor, which is equal to zero. Note here that your di over dt is negative because you have a decreasing current. Now, solving for I from this equation, you have your I that's equal to negative L over R di over dt. Let us separate your di with your dt and then integrating, just like the process that we did earlier. We have your I that's equal to I naught e negative e R over L t. So we evaluated your current from, or we integrated your equation for the current Pi and then for the time dt. Here your I naught is the maximum current before the switch is closed. So you have the current I that's equal to I naught E negative R over L times T. You have here an exponential term. And if you're going to graph the current decay, this is how it looks like. So you have an exponential decay of your current, which is asymptotic with your time axis. So this is again exponential decay because of the exponential term in your equation here. This is your current decay in your RL circuit.